My name is Ramon Barea, and I am presenting Myceliotronics, understanding and utilizing the naturally occurring bioelectricity within mushrooms. So as a prerequisite, I wanted to just cover some basic concepts that we'll go over. One being Ohm's law over here on the right, the triangle, V equals IR. We'll see that over time, some of the tests I performed, resistance will increase, and because of the relationship with resistance with voltage, we will see voltage drop as resistance increases. We use this equation a lot overall throughout electrical engineering. Also, I want to cover frequencies briefly because we'll see differences in frequency over time within some of the plots. Essentially, what we'll see is that we can read a singular signal over time, and it looks something like this in the time domain, where there's multiple signals being collected together in once. But when we look at the frequency domain, we can see the actual impact of each specific waveform creating this signal that we first saw. This allows us to actually understand what's going on underneath when we actually test these things. And the same is true for light. So I've experimented with UV light this time around, but there was dilution from visible light from a nearby lamp because of my testing parameters. And that'll come into key later, but it's important to acknowledge that it is also a waveform, just like the electrical signals being discussed. I also wanted to take time to make sure I explain what mycelium is in the first place of a mushroom. And myceliums are basically the roots of all mushrooms, where in the first few days, we plant it into the substrate, it's barely visible. We have to give it perfect conditions so that it can actually grow. But around 8 or 9 days in its incubation, we can see that it's actually grown, it's flourished, and it's ready for testing. So why is mycelium conductive? The concept of mycelium being conductive can actually get its own presentation entirely. But the main concepts to understand is that there's ionic conductivity from specific materials within the mycelium. There is a network-like structure that allows like water and these ions to pass through. And the denser the mycelium becomes as we allow it to grow, the stronger these electrical connections become, and that it has concepts like mem resistors. Essentially, when one part of the network is experiencing a certain amount of resistance reacting to something, the rest of the network will also display that same reaction. So I did a big portion of my internship just researching at the beginning of what different papers, what other individuals have done. So one interesting concept that came up was mycelium skin formation. Now this was interesting because we create this very thin layer of mycelium and then we embed electronics onto it. And the purpose is that we can make these PCB boards that will degrade over time as opposed to having it last for years and years. Then we can take those electrons and then reuse them. We can also create batteries. So we can take those sheets, we can create a dry packing sheet, put a gold plating, another dry packing sheet on the other side, and in the center, soak mycelium with electrolyte liquid that a battery would normally have. This is an example of a zinc carbon battery at 1.5 volts. So if we put two of these batteries together, we get 3 volts, and that allows us to run basic microcontrollers for actual circuits you would see in the real world. This paper went on to discuss essentially an impedance sensor. So up top in section A here, we see two batteries that power this whole circuit at 3 volts. We see a small Bluetooth module, and we see this trace of metal. And those traces essentially increase in their capacitance when you touch it. So every single time you touch the sensor can read this and send it out to a receiving module. And over time, the creation of this only lasts about 11 days. So this is amazing for concepts where we only want a circuit for a temporary amount of time, as opposed to like having it, creating something just for a day and having it last 1,000 years. It's very important to understand the biodegradability of a concept like this. Then I went on into another paper. It's from an individual named Anad, who has given us amazing research to go off of. And one of his first tests here was acknowledging just the bioelectricity that naturally occurs within the mycelium here. So here we see two different petri dishes, and what he did was just connect them and just over time see how much the electricity drops, how consistent it can be, how deterministic the noise can be, and what could we expect when we actually try to make an actuator out of this. He then attached it to this robot over here. And essentially what this robot does is when UV light is shined upon it, the resistance increases in the Petri dish. And because the resistance increases, electricity cannot flow as much. And because of that, we can send this signal to an Arduino and create motion. So that way it knows, oh, there's UV light shining, do one impulse action. There's no UV light shining, do the other action. And all the Arduino does, it controls this pneumatic system that pumps fluid and allows this robot to stand or sit down. And here we actually see that behavior where the UV light shines, the robot sits down and stands up, and it was able to be repeatable over time. And what was important was that we had to amplify the signal because typically it was in microvolts and we needed it in millivolts. So now going on to my personal research. So the hardware used, thanks to UMass Boston, I was given an analog discovery 2 to perform various tests, and I was able to use this INA 333 operational amplifier to amplify the signals from the mycelium so that I can actually read it. When I first tested the mycelium, I tested it as a resistor just to see how much it would resist electricity flowing through it. And it gave me about 300 to 500K ohms, depending on what points I actually read from. So I had to start off with just the substrate. What the mycelium is actually eating, what it's actually sitting on, is potato agar. So the potato agar itself, without any form of mushroom, had 33 to 56K ohms. It had very slight UV light response. So when I shined UV light onto it, I could see it increase in microvolts. And then as I turned it off, I saw a decrease. And this was replicatable, but it wasn't a major impact. So when I see UV light responses going on, I know it's more towards the mycelium than it is toward the substrate. And I was able to then send a standard sine wave through it, and I was able to witness the pattern of the sine wave itself. Though the wave itself seems to be shifted downwards, and that seems to be based on the probing points I have used. And this was my first attempt at probing anything, so doing my best to learn and how to actually properly do this. So, but it ended up yielding some interesting results. Now we go to the king oyster mushroom and the official UV light sensor testing, reminiscing that it had 300 to 500 K ohms. And it's a nice close-up view of how seeing the actual steel electrodes actually connecting into the mycelium, as steel works better for mycelium compared to like copper and other materials that it won't exactly love to hug onto as much. So the naturally occurring bioelectricity of my mycelium when I had the operational amplifier equipped was 100 millivolts. This was very steady, and we can see the frequency responses that there's not too much noise going on. There's a few little spikes here and there, but this is a very steady circuit going on within the mycelium. So then we have 220 seconds of UV light. At first, there wasn't too much of a response, but then as we go forward in time, there was a linear response downwards. As we could see, we're slowly going down to around 20 to 30 millivolts, and it continues to degrade over time. We see changes in noise a bit because of the influence of the UV light itself. And the most important part was removing the exposure of UV light. After about 60 seconds, we were at like basically the bottom. And over time, it was just kind of recuperating from the fact that it had such intensity UV light shed upon it. But eventually, what Anand had seen within his imagery was that these spikes occur. And these spikes signify that the mycelium has recovered again. And this is what would be used to actually determine when the robot would stand back up, is this particular impact of spikes. But with the methodology I've been using with UV lighting, I believe it's better to use blue light closer to the UV light spectrum. Because what I've noticed over time is that there was a drop in the bioelectricity over time when I tried to repeat this test. And eventually my mycelium stopped responding as much to the UV light. And that is because UV light can be damaging to biolife in general. We wear sunscreen for that same reason. So there is more testing to be done by understanding what best magnitude of light frequency to use. So my next test was an 8-hour natural bioelectricity test. So this led to a very interesting result. Essentially, I set it up, I left it alone, and just read the voltage over time, and it continued to increase very steadily. But what ended up being very interesting about this was that it gave it polarity. Now, polarity is interesting because after 8 hours of this, it seems like the ions in the networks essentially grew into that direction so that electricity naturally flowed in that direction. So I repeated this many, many times. And when I put voltage, the positive lead on this particular electrode, I would get a positive signal. And if not, I would get the negative. So I essentially shaped the mycelium by reading it over time. And that is interesting research for anybody who wants to grow mycelium for specific sensor needs. And now the importance of a Faraday cage as seen with the spectrograph. So for a moment there, I had gotten excited when I was pressing the switch and I was looking for small, small impulse responses from the UV light into the mycelium. And I saw these little spikes. And I thought, is this the UV lighting? But I had fear that there's an electromagnetic interference from the light itself, as opposed to it being the UV light response. So I disconnected the electrodes from the mycelium and repeated the test, and I saw these little blimps again. And I saw, okay, yes, that's electromagnetic interference from my switching components of this UV light. Good to know, mistakes happen and we keep on going. But that's the reason why Anand had used the Faraday cage, because we're trying to measure such small voltage that any little bits of interference and noise can ruin our results. Now, circuits with mycelium, seeing the MEM resistor behavior with Ganoderma sicily. So when I read this particular chunk of mycelium here, this is a different from King Oyster. This is its own concept, and it had about 30K ohms resistance. So what I decided to do was to set up two LEDs. I put three 10K resistors in series, that's what I had on hand, and on the other side, I ran electricity straight through the mycelium and through the LED. LED requires a resistance at first to protect it, and essentially, when I turn the circuit on, both of these are receiving 5 volts shared, and they both lit up. What was interesting was at first, the light with the 3Ks was a little dimmer than the other one, which is run off purely from the mycelium. But over time, they evened out, as if to say that over time, the resistance change within the mycelium in a steady rate. And this can actually lead with more testing towards understanding MEM resistor behavior of how it maintained this. Because then as I turned it off and turned it back on, the same process was witnessed where the LEDs were now about the same luminosity. And just to make sure that it could run by itself, I disconnected the resistors and just tried one LED. And essentially, this mycelium can run purely by itself with 5 volts to power something like this. So now we have pure mycelium circuit and differences in stored charge. I used the original King Oyster on one side, and then I used on the other side the Ganoderma sicily, and they were both able to power an LED. Well, this one little interesting response was unique to Headfield. You see the LEDs come on, and you see the sesame power up a little bit later. It seems like it stores charge a bit better. And because of that, I believe it has better applications toward a capacitor in a future circuit. I did not get to the capacitor yet, but it'll lead to future results, and I hope to do it in the future. And drawn out of mycelium, one of my final concepts. What we had done here was pack a mycelium into essentially a PLA molding, and we had to pack the propellers within the molding and leave it over time. It sat about 5-6 days and then was baked at 170 degrees for about 7 hours. And I placed this center molding in here as well so that I can put heat inserts and allow expandability in case I want to create a cover for the controller modules. But overall, it was found that the drone was a bit too heavy to fly, but the propellers all worked. It survived the process. I just have to do some subtractive processing, and eventually this will be up in the air. So that is the end of my presentation. I just wanted to take the time to thank UMass Boston for the Analog Discovery 2 and for all the knowledge they have given me. I had many questions, as a lot of this was new to me, to Blue Marble Space Institute of Science, and to get me into this opportunity. MIT Media Lab for providing Potato Agar and amazing advice. MIT AVT, who has supported me throughout the entire process. NASA Ames and the Bioaircraft team, who have been amazing to collaborate on this type of project. And my friends and family who are currently watching as well. Thank you, everyone.
Wow, that's wild. That's an awesome
Yeah,
presentation, Ramon. If we
thank
have
you.
any questions, we do have time. We can ask a question or two here. Sanjay has his hand up.
Ramon, this is a fascinating presentation. I really hope your drone takes flight. I had a question about the mycelium because you use different mushrooms and their mycelium to generate electricity. Is the mycelium the same across the different mushrooms, or do different mushrooms have different myceliums, which might be beneficial or not for certain circuits?
That is the interesting part. So right now, we're trying to create a standard with Ganoderma sicily as a base mushroom to test a bunch of different concepts because its mycelium has specific unique properties. And Dr. Perez can go in great detail about how amazing sicily is. And we chose Oyster specifically to go alongside it because that was a Nod's project, and we wanted to replicate his work as well and gain a deeper understanding. But mycelium definitely has different properties, and there's a lot to learn from each different breed and species.